Okay, let's go ahead and get a clean page. So I'm going to do this first video just on 1 through 5, which is the conditional probability and independence section on the review. Okay, so first one, let me put this in tablet mode. Sorry about the noise. So first one, number 1, the equation we're going to need here is the probability of A given B is equal to the probability of A and B divided by the probability of B. And in this case, for your number 1, it gives you the information that the probability of A and B is equal to 0.4, and it also tells you the probability of B, right? So it gives you all the information you need on the right side of the equivalent sign. And so we can just fill this out as 0.4 over 0.9, and probably just simplify it as 4/9, unless it wants a decimal, but if it's a handwritten test, I'm sure that's fine. So that is number 1. Number 2, it starts bringing in the total law of probability, which is the probability of A, and you could think of this as the tree diagram, and I'll draw that out here shortly. So probability of A given B times the probability of B, plus the probability of A not B times not B. So this is number 2. In this case, right, so let's look at the tree diagram. Think of that B is happening first, right? So like B can either happen or cannot happen. And from our word problem, it tells us that or not word problem, it says, from our problem, it says the probability of B is 0.4, which means that not B is going to be 0.6. And it also tells us the probability of A given B. So this is A given B, right? We're already over here, is 0.7. And for this problem, this is all we care about. We could do B. We could do this. We could find this, but this isn't really necessary. And then the other one is going to be the probability of A not B. So A not B is equal to 0.5. And again, we could do the other one as well, but we don't really need it in this case, right? So now if we're looking for the probability of A, we're just going to go look where A is occurring, right? In this case, it's here and it's here. And so the equation is exactly what we have above, is we're going to go, and we can reorder this, right? We have A given B, 0.7, times, well, we have to travel down this branch, which is 0.4, plus, and now we'll look at our other branch, right? 0.5 times 0.6. And this ends up getting us 0.58. Okay, so that is number 2, right? So either the tree diagram or the equation there works. Let's look at 3, and again, feel free to pause, stop the video, rewatch. 3 here, it says, roll a fair dice, suppose A and B are 2 independent events. And so it's really just testing us on the definition of independent events, right? The probability of A and B is equal to the probability of A times the probability of B. And so in this case, it says A here is rolling a 3 the first time, rolling a 3. And we know that the probability then of rolling a 3 on a normal dice is just going to be 1/6. And it says B is also rolling another 3 the second time, so rolling a 3. In which case, it is also, oh, this should be a B. It is also 1/6. And so all we have to do here is just 1/6 times 1/6. 1/36. Right, so independent events, we can just multiply the probabilities together. I think 4 was a little bit of the tricky one, right? It helps to draw out the nice tree diagram. It says 2 distinguishable fair die are rolled. One is red, one is green. Let A be the event that that the red die is 2 or 4. So red is 2 or 4. And so that gives us, right, these two possibilities. 2, or 4. And it says let B represent the sum is equal to 6, right? So when I roll a 2, right, let's say this is my red die, and then I roll my green die. So I'm saying my red die is a 2 or a 4. Right, given that this has happened, and I think you did this drawing as well, right? We have our 6 possibilities, right? 1, 2, 3, 4, 5, and 6. And so the only one that adds up to 6 here, right? We want the sum to be 6 is this 4. And same thing over here. Right? We have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And again, there are 6 possibilities here, and the only one that we really want is where they add up to be 6. So 6 possibilities here, 6 possibilities down here. And in each case, right, the one that we've circled is really the only one that we care about. So we have 2 possibilities that work, right, the highlighted ones here. And we have 12 possibilities total, so it just simplifies back to 1/6. And let's do one more. So number 5 says there is a 30% chance of rain today and an 80% chance of rain tomorrow. Assume that the event that it rains today is independent of that it rains tomorrow. What is the probability that there will be no rain? So we'll just say probability of rain today, well, that's equal to 0.3. That means the probability of no rain today, we'll just say rains today with our little dash here, it's not going to happen, is 0.7. And it says the probability of rains tomorrow, you could probably figure out better notation than this, but tomorrow is 0.8 or 80%, which means the probability of no rain is 20%. And so if we want to figure out there's going to be no rain today and no rain tomorrow, and we know that these are independent, then that means we can just multiply these two numbers together. Actually, I lied. We're going to do 10 problems, or whatever Bayes' theorem goes up to, since it's only been a 7 or 8 minute video so far. Okay, let's go ahead. We're looking at 6, which gets into the section is now called Bayes' theorem, right? As a reminder, Bayes' theorem is the probability of A given B is equal to, you're going to write the opposite, B given A, times the probability of A all over the probability of B. So we'll probably need this here. It says use the information in question 2 to find the probability of B given A. So we actually want to find this now in our problem 6, saying use whatever information. We'll have to go look at 2 here in a second. And so now we want to get the information of this. And it's very similar, right? The A's and B's just change places. Right, and I'm only doing this because it's telling me in the problem, solve for this. And so if we go back to 2, right, 2 tells us, this is given information. It says 2 tells you that probability of A given B is equal to 0.7, and probability of, what do we need? We need probability of B is 0.4. And remember, we solved for probability of A, which was using the total law of probability. That was the 0.8. So this is from, right, this is the actual answer from number 2. And so if we have all that information again, we can just plug everything in. This ends up being 0.28 divided by 0.58. And I'm not going to pull open the calculator app till later when we actually need the TI-84. I'll just do this on the side. We have 0.28 divided by 0.58, which should be 0.4827. 4828. 0.4828. Okay, let's look at 7. And it says all these use a tree diagram, and I think you prefer the tree diagram, so that's what we'll do. It says that the residents living in the dormitories at a university, 58% live in the West Hall. All right, so West Hall is over here, 58%. And I think it just says everybody else, they live in the South Tower. So in this case, right, the complement would be 0.42. A sandwich shop randomly mails a coupon for a free sandwich to 26% of those in the West Hall. So given that you live in the West Hall, the coupon, right, to the West Hall is 0.26. And we could also say no coupon, given that you're in the West Hall. Unfortunately, these people are 0.74, right? They did not get a coupon, even though they live in West Hall. And I think it says 19% of those living in South Tower got the coupon, which means 81% of the people living in South Tower did not get the coupon. And now let's read. Now that we have this, it should make it easy. A student living in the dormitory is randomly chosen. Find the probability that the student does not receive a coupon. And so we're looking for the probability of no coupon. And so let's go look at every word that has no coupon. Right? We have this one. We have this one. And so now we're just going to travel down the branch that we want to find the coupon. Or to find the no coupon, right? So we have, if we're in West Hall, there's a 58% chance we live in West Hall, but there's a 74% chance we didn't get the coupon if we're in West Hall. And there's a 42% chance that we live in South Tower, but there's an 81% chance if we're living in South Tower, we don't get that coupon. And so, again, just if we draw the entire tree diagram, it should allow us to answer any possible question that they give us. And let me do the math on the side here. I got 0.7694, and I would double check. I think this is, I'll double check my work at the end with the answer key, I guess. Number 8. Give me 1 second. This was the weird wording question. Let me scroll down here. I guess let me also make sure the answers. So far we have them all. Number 7, yep, perfect. 0.483, 0.14, good. We're all good on our solutions. Okay. Number 8. It says a professor insists that senior physics majors take his notorious, a lot of noise there, take his physics aptitude test. The test is so rough that anyone not going on a career in physics has no hope of passing, where 40% of the seniors who do go on to a career in physics still fail the test. And so it gives us our information kind of backwards here, because then in the next sentence it says 95% of all senior majors go on to a career in physics. So we actually want, we'll say physics career, and we'll just say not physics career. Right, it says 95% are over here, 5% are over here, and then it also says only 40% of the seniors who go on to a career in physics still fail the test. So given that you do go on to a career in physics, so this is given, right, the fact that you fail is equal to 0.4, whereas the fact that you don't fail, or you could say pass, right, it's really up to you, but I'm just using their words, don't fail, physics career, would be 0.6. And then the wording here was it's so tough that anyone not going into career in physics has no hope. So the fact that you're going to fail is absolute, right? You're going to fail 100% of the time. The fact that you're going to pass, or the opposite of fail, and this should be this, right, is going to be 0. It says, assuming that you fail the test. Okay, so given that you're going to fail, we're going to write that. That's another way of reading that. Assuming that you're going to fail, given that you're going to fail the test, what is the probability that you will not go on to a career in physics? So no physics career. So this is what we're looking for. Let's make sure I'm reading that right. Assuming that you fail the test, what is the probability that you will not go on to a career in physics? Yes, okay. So right, this is going to be the opposite, probability of failing, given that you did not go to your physics career, times the probability that you have your, or probability of a physics, not being a physics career, all divided by the probability of failing, right? And so think of this like as a proportion, right? In the numerator here, it's asking about the people who are not going onto a physics career that failed. And so that is these people over here, right? Failed 100% of the time, no physics career. And so that is our numerator, right? That is 0.05 times 1. And now we want to see that's a proportion of all the people that failed. So we're going to find all the people that failed. Well, the people that failed again are going to be this subsection. So we'll just write them again, right? The people that failed from the non-physics careers. But we also need to add up the people that failed in the physics careers as well. And those people are over here, right? 0.95 times 0.4. Nope. And so let's go ahead, we'll pull out the calculator here. We don't need to do the first part, right? 0.05 times 1, easy enough, 0.05. And so we have 0.05 times, or plus, we have 0.95 times 0.4, enter. And so now we can just do our math. All right, we'll add 0.5 to this, 0.05, sorry. And we'll take 0.05 and divide it by 0.43. And we get the correct answer, 0.11628, I guess. And that was number 8, right? So again, getting used to those tree diagrams. And we'll do one more here, and that'll take us to discrete random variables. So number 9. Again, same type of idea. We're going to need a tree diagram. It says a motor insurance company insures drivers in the age group A, B, and C. So we'll say we have A, B, and C, right? Let's actually write it this way. With our, let's get a bigger, there we go. All right, so we have A, B, or C. And it says A happens 40% of the time, B is 25%, and C is 35%. Okay, the company's record shows that each year 2% of the customers in the age group A, so make a claim. And so we'll say claim, we'll say CL given A is, this is going to be 0.2, which means no claim, given that you're in A, is equal to 0.98. For B, it says 1%, and so 0.01. You made a claim, given that you were in B, which means there's a 99% chance you don't make a claim if you're in B. And finally, C is going to be 1.5, so 0.015 is going to be a claim, given that you're in C, which means 0.985 is no claim, given that you're in C. And now we just need to read this. It says, given that the driver made a claim, so given that they have made a claim, what is the probability that the driver is from group C? So C given the claim, right? So by Bayes' theorem, we have probability of claim given C times the probability of C, all divided by the probability of a claim. And so now if we're just considering first in our numerator the people in group C that made a claim, right? That's who we're interested in this proportion. Well, the people in group C that made a claim is this branch right here, right? 0.35. And I'm going to write it the other way just because it'll be in the same order as our equation. Right, 0.0, if I can get this to work. There we go. 0.015 times 0.35. And now if I'm interested in all the claims, right, all the people in my denominators, anybody who made a claim, well, it's, right, we have claims in A and B, so we need to travel down a few branches, including the same group that we went down in C, right? We still need that total number there, so I always just write the first one that's in the numerator again. So here's the people that made the claim in group C. I need to add up the people in group B that made the claim, which would be 0.01 times 0.25. And then I need to go grab the people in A as well. Sorry, I know this is getting smaller. The people in A, right? 0.02 times 0.4. So let's go ahead. Our numerator should be 0.015 times 0.35. We had a very small number. Yeah, I think this ends up being a very, right, we end up having to do the old trick of add one and then see what the decimal is. So 0.00525 all over we have 0.01575, and so we just need to take those two numbers now and divide. No, maybe it's a nice number, 0.3333, right? Dot dot dot. All right, so final answer, that takes us to 22 minutes, right? So that's questions 1 through 9. And then on the next one, I'll pick up starting at 10 and I'll get all the way to 20 at least. And I'll send out that video to you as well. All right, so I'll see you in the next video.